automatic recording of on Collaborate or whatever.
No, we have that for certain lecture rooms for only during the lecture time.
Okay.
But
Yeah,
because we're not officially a lecture.
we can do ad hoc recordings. It is a pain in the ass to attach it to some pre-existing lecture series.
All right. We're now sharing. Right. Is that record? No, stop share. Did we start recording? Resume recording. There we go. Now when can it start?
Okay, thanks. Josh? I'll have to stay near the microphones, all right? I tend to wander around. If anybody's in my lectures, I can wander around the whole room. I'll do my best. Okay, so thanks very much for inviting me. It's great to be here. First thing to say before I forget is that a lot of the work I'll show is going to be pilfered, for the lack of a better word, from a variety of people I've collaborated with in no particular order there. Other people, well, of course, Josh is there and Trevor, of course. I should mention that I worked a lot with Paul Bishop, of course, who died just over a year ago now. And the other person that I find remarkable in Glasgow, none of you really are old enough probably to remember him, is a guy called Chris Wilkinson in electrical engineering, who was just an amazing, absolutely amazing scientist. So I had this really nice, ambiguous title of the talk here, How Well Can We Know the Ancient Geomagnetic Field? And I do realize that could mean almost anything, but I wanted to at least try and get a few people in the audience. I better, oh, no, it's going to work. Oh, do we have a way of progressing the slides? It's going to be a very short. Here, oh, we need a minute. Oh, is it? Oh, that seems weird. Yeah. Here, I'll okay, you get to, I'll advance slides. Okay. That's it. It'll be like being person a talk on domineering. Okay. All right, so the next slide. Oh yes, no, that's fine. Sorry, the previous slide. Right, so that's more a descriptive title of the talk. So I'm going to look at the recording properties of inhomogeneously made by fine particles, which probably sounds very esoteric. No, not yet. No. So I was going to say that it's really hard to underestimate the value of magnetic recording in fine particles and the unique data set that can reveal from the history of not just the Earth, but the solar system. This is an image I've taken from the MIT group. And this is showing the recording of the magnetic field in the protoplanetary disk going back 4.5 billion years ago. And despite the great advances in astronomy, really paleomagnetism recorded in meteorites is still the best way to get the spatially resolved morphology of the protoplanetary disk field. And that field, of course, is essential to enable the accretion of mass in essential for building planets. So that's one aspect. The other aspect, next slide, is the motion of the continental plates. This is something that maybe paleomagnetism is most well known for. And of course, in the 50s, 60s, and 70s, really a lot of work went into trying to map out the motions of the continents. With the increased resolution and the different experimental techniques, that work is still ongoing. This is a picture from a paper from last year from Alex Brenner and Roger Fu from the Harvard group, who are looking at some really old material from Western Australia, about 3.35 billion years old. And their analysis of the magnetic signals in those cratons was that they had mobile lid or active lid tectonics going back to that time. So, you know, we had this tectonics going back 3.35 billion years old. Not only does it show us about the thermal history of the Earth, but it also tells us that if they've done their analysis right, it implies a stable dipolar magnetic field. It also rules out this silicate geomagnetic field that was supposed to have been created in the lower mantle. So we had a core dipolar field that was steady even without inner core growth. So lots of interesting things cannot be obtained by any other way, and it all depends on our ability to interpret the signals recorded in the submicron nanometer scale, mostly iron oxide magnetic particles. Next slide, please. Now, when we do the paleomagnetism, not that I do, but other people do, they go out into the field. This is a picture I stole from the Liverpool group. Go out in the field, you collect the paleomagnetic samples. Sometimes you aren't them, normally you would. You come back, you put them in some magnetometer, and you get some data out. In order to get paleointensity, what we have to do is to measure the original magnetization of the sample, and then you remagnetize it in the laboratory, in the laboratory field. You do this over a number of different temperature intervals. Hopefully you come up with a nice straight line, and you get an estimate of the ancient field, which is proportional to the ratio of the laboratory magnetization and the original magnetization. So magnetization loss divided by the magnetization gained in the laboratory, multiplied by the laboratory field. So I have to say, paleomagnetic samples that give such a nice straight line are pretty rare. More often, they look like this. I would say this probably is certainly more frequent than I saw the previous slide. So they're a bit of a mess. These would have been rejected by standard protocols they have for estimating the reliability of the sample, but there's no reason necessarily why these samples give this poor behavior. Quite often you'll get a sample that gives this poor behavior, and you have a sister sample right next to it that gives a much better result. We don't really understand why this is. Other samples, other measurements are less ambiguous than this, and the decision of whether they're a good sample or not is difficult. And so you have big databases of paleointensities, paleomagnetic information, and you decide yourself what criteria you want in order to say they're reliable or not. But generally, you know, if you select a reasonably wide selection process, you can get this scattering of data. This is the scattering the dipole moment as a function of age. That's fine, next slide, yeah. And from the same data set, if you choose different selection criteria, then you get a very different interpretation of the geological history of the Earth. And just one example here is an effort to try and determine when the inner core of the Earth nucleated. And so we had this data set with a selection criteria from Andy Biggin in the Liverpool group, published in 2015, who said that the inner core nucleated about 1.5 billion years ago on the estimation that we get a large, or we perceive a large increase in the geomagnetic field generated by the partitioning of the lighter elements out of the core. So that extra energy putting into the convection in the outer core produces a more intense field. Essentially the same data set with a few more data points from Bono's group, and he has decided that his data estimates the nucleation of the inner core of only about 500,000 million years ago. 500 million years ago. So quite a big difference in the age of mutation, basically from the same data set, filtered on different criteria. The problem is that the data is just very poor, and there's a very large amount of scatter. Next slide. So this is one of my first slides. It tells us about the reliability of recording in a particular mineral as a function of grain size. And everything that we do in paleomagnetism relies on the theory that describes the magnetic properties of stable single-domain grains. These are the simplest type of grains that are small, uniformly magnetized. You can describe their theory pretty much analytically. Done. And it actually describes the recording process very well. It was first dreamed up by Neal and Stone and Wolfbach in the 1950s. And it's been validated many times, mostly on materials which we know are single-domain. It basically works. Next slide. The problem is that those simple analytic calculations also tell us that. Do
you want to do this one?
Yeah, also tell us that the minimum size for a stable single-domain grain, say for magnetite being one of the most common paleomagnetic recorders, is about 40 nanometers. The largest size, is about 80 nanometers. And we know that the grains we have in our samples are going to be outgrid that range. You might get some in there, but you've got many that are not. People have known this for a long time. So they came up with a nice term called pseudo-single-domain grains, because there were grains that behaved like single domains, but we knew they couldn't be because they were too big. Unfortunately, also along with that name is we assume that they behave in the same way. We applied the same single domain theory, even though we knew they were not single domain. Shortly after the single domain theory came up, or 20 years later, in the 1970s, Dunlop and Day produced this so-called Day plot, which I got into a lot of trouble recently about, which shows the saturated remnants against the ratio of co-recipient remnants divided by co-recipient. So it's the thermal stability on saturation remnants really divided by its field stability. And Day came up with this way of describing the domain state of particles depending upon where they fitted on this plot. And single domain, you can theoretically tell where they're going to be. Multidomain, here somewhere. Everything else will single domain. And I can guarantee you 99 times out of 100, 999 times out of 100, you measure a paleomagnetic sample, it's going to pop in this PST So we need to understand what these pseudo-single domain grain samples are, what their magnetic structure is, and how they behave in terms of their long-term stability and development. Next one. So this is one of my favorite papers ever. It's called The Hunting of the Sark. It's a paper by David Dunlop. I think it's expanded in his book. And it refers to this poem by C.S. Lewis, The Hunting of the Snark, which some of you may have read. Anyway, this snark was this unimaginable creature that everybody claims to have seen, and there's a different description every time they see this beast. And it's hunted by many, but nobody seems to quite get a handle on it. And that, to David Dunlop, who wrote this paper, was very apt for pseudo-single-domain grains. Everybody really wanted to know what it was. Everybody looked at it with the analytic theory, which was available at the time, came up with a different answer. Next slide. So one of David's solutions, which is right, I have to say, is that these pseudo-single-domain grains are formed by these lamellar domain structures. So we have domains and regions which remain uniform and parallel to each other, but these uniform parallel regions rotate with respect to each other. And in particular, you have two domains which are anti-parallel. You have something in between called the domain wall, and that domain wall was free to rotate and carry the magnetic signal independent of the domains on either side. Of course, that will only ever work you had odd number or mean number of domains, not number of domain walls, otherwise everything would transpire. So it is only ever a thought experiment. It clearly didn't work. No evidence for such particles. One of the main problems, even in the 1977, it was very difficult to image these, which is why people like Josh and Trevor are so valuable, because they now can image these days. But you know, we weren't able to image these structures, so it's a pure guess as to what they were. Next slide, please. So, this is an advert for what to do properly. Okay. So, what you need to do, clearly now we have our computers and we're able to model magnetic structures using finite element or finite different techniques. Then we can determine what the real structure is inside these fields. We don't have to rely on these analytic theories. And this is a piece of code that I've written as open source. If people want to play with it, this is used. I named it after a guy called Wyn Williams. Wyn Williams was a famous geophysicist in the University of Washington. And he came up to me when I first worked on this code and said, I don't believe that code. You never get anything out of it of the numerical model. So that's why I named the code after him. And he's right, of course, but the point of using a numerical model when you're looking at interactions between lots of nonlinear systems, but you do the physics, you can't get any more physics out of it than you are able to elucidate the trends as a function of different parameters that you ingest in the model, and that's the important thing we're trying to get out. Oh, okay, next slide, please. This then adds to my other most favorite slide, which is a quote by George Box. Anybody know who George Box was? Okay. He was a famous British statistician who spent most of his time in the States. Well, he was a statistician, so as we all know. But one of his famous sayings, which he repeated in many of his publications, is that all models are wrong, but some are useful. And in everything I publish, I remember that, because all models are, to some extent, an approximation. We're not trying to simulate fine detail of reality. It's an impossible task. But we hope to cover as much of the detail as possible so that the models are useful and they elucidate some trends that we can validate in some other way. They're a model that allows us to be predictive in some way and understand it according, in our case, according to reality of magnetic systems. Okay, I'm usually pretty much that grumpy. So today's okay. Exactly. Okay, so in these numerical models, I'm going to show you a number of different solutions. So the first thing to show is this basic structure here, that once the true nature, once you get bigger than the critical single domain grain size, the grain becomes too big to hold just a single uniformization. Then you get into this vortex domain structure. You know, you look at that now and it looks pretty obvious to me what else is going to be. David Dunlop, who is one of great mentor of mine, really still believes these are exotic domain states. I respect his view, of course, but I think there's lots of evidence, which I'll show you, that these are definitely not exotic in any way. I'll show you a number of these solutions, present them in different ways. So this is just the vector direction that we find inside particle, colored by some mechanism, colored in this case by its relationship to a crystalline anisotropy axis, and according to helicity and so. So this shows a vortex core, high helicity in the center, and actually the remanence, the signal in the particles carried by this remanence core is vortex core. Sometimes I'll put an isosurface of vortex core, and otherwise I'll color the surface according to the anisotropy. So blue, then it's aligned with the easiest anisotropy axis, and red when it's colored on the hardest anisotropy axis. So what I'm going to do now is to show you a series of images that show how these magnetic structures change as a function of grain size. So I see, thinking I was going to do this myself, I didn't put a video in.
It's all
So
right.
there's like 20 individual slides.
All right.
So you just run through them. I'll stay there for a second. So this is the smallest grain size, 0.2, 200 nanometers. It shows a well-formed vortex core that I'm just showing the orientations of. So this is the top image is the one to keep an eye on. So if you run through the next 5 or 6 slides, you can see that this vortex core grows, and eventually it grows into a quite complex shape. Yeah, that's one complex shape, which moves the grain from a single domain through the pseudo-single-domain grain size vortex stage through to what I would call reasonably well-defined multidomain grain. My definition of the multidomain grain is that they have these boundaries between domains that are of a well-defined size that you can calculate analytically, assuming the part was dominated by what we call geostatic forces. Paleomagnetically, what it means is these are grains that no longer contribute to magnetic forces. They contain so many domains where their orientation is controlled by these magnetostatic forces, and they have really very good influence of the external field which we're trying to control. So we've managed to model these structures from the smallest grains up into these multi-domain grains, seeing that the single vortex is dominant. The next slide, please. So the single vortex in dimensional magnetite, it stretches from about 80 nanometers up at least to 1.5 microns. So that's an order of magnitude, at least an order of magnitude, bigger than the single domain grain size range, which is this region in red here in this diagram. So this blue is something what we call unstable, super-paramagnetic. Red is this single domain region of which theory, analytic theory, still apply to interpretation of paleomagnetic observations. And this green region, and maybe a little bit more, is where these vortex states sit. So my suggestion is that paleomagnetism that record the signals of the motion that comes in any other paleomagnetism designed to understand is recorded predominantly in these vortex states, these so-called pseudo-single-domain grains, but we know now are vortex states. So next slide. Okay, so you notice I did those in terms of a very well-defined morphology, a cube octahedral grain, because that in the free system is what magnetite crystallized in. You don't have to do that. So people like Josh and Trevor will do these incredible experiments where they can do a focus ion beam slice and view. They can reproduce these three-dimensional geometries. You have to guess what each of these represent. Would you say that was a duck or a bunny rabbit? I had a big debate with my other senior academics. You can produce the morphologies of these grains. And next slide, you can also model these, of course, this is finite element model. Next slide. And again, these consist of one or more vortex states. However you want to do it, whatever grain size. Not only magnetite, of course, but iron, greigite, even pyrrhotite. I'm not sure how many different magnetic minerals you would mention, but everything pretty much, unless it's incredibly high anisotropy, will be in these vortex states. All right, next one. Validation. So this Trevor will recognize this. Validation of this is important, particularly in the early days when you have prestigious people like Wyn Williams and David Dunlop who didn't believe what we were suggesting. So this is some of Trevor's work where we have the contrast image of a magnetite grain and then the off-axis electron holographic image of the magnetic structure below it. So in electron holographic imaging, essentially these contours are parallel to the magnetic induction field, the inside the grain, so they give you some indication of electron magnetization. This is our reconstruction of the magnetic morphology of that grain. the prediction of what the magnetic structure inside that would be, and then the simulation of the off-axis holographic image. And I think it's a pretty good match, personally. And there was another colleague of mine who was supposed to come up and give a talk, and I showed him these images, and I was really, really pleased how close they were. He said, "Yeah, but you know, you've got more yellow here than you have here." I'm sorry, that's an excellent match. Whichever way you look at it. Okay, next slide. We can try to validate other mineral systems, other techniques. This is magnetic force microscope. People not familiar with magnetic force microscopes. It's essentially a small needle on an arm with a magnetic dipole at its end, and you measure the attractive force that that needle has to the sample which you are scanning. To scan over the surface of a crystal, and you build up a signal or contrast depending upon the repulsive attractive force at that point on the surface of the grain. This case was a TM50 type of magnetite. These are the experimental observations. This is the micromagnetic balls. These are still vortex states essentially, slightly more complicated. And so these are our predictions, and these are our simulations of the magnetic force microscope. And again, I think they match pretty well to the observations. So that's to convince you that everything else I'm going to say, which is pretty damning in some ways, does have some validity in the models that we have, models of magnetic structures that we've been developing. All right, next slide. So, in paleomagnetism, a key concept is this idea of blocking temperature. So this relates to the stability of the magnetization as a function of temperature. So if you imagine a rock that we cool over time at high temperature, the magnetization can flip between one direction and another. This is just shown as a single domain grain, but it can rotate from one direction to another direction because an energy barrier has to overcome. At high temperature, this energy barrier is very small. As you cool the sample down, then this energy barrier increases, and the relaxation time, the amount of time that that sample takes to rotate from one direction to the other, increases, and it increases exponentially with the energy barrier. And this energy barrier itself is decreasing as a function, is increasing as a function of cooling temperature. So when you cool it to some point, it's no longer able to overcome this energy barrier, and it remains frozen at this blocking temperature. So that magnetization, that grain, is blocked in the direction of the ambient field, essentially, at that blocking temperature. So that's a key thing you need to remember. Next slide. For single domain grains, you can do this on the back of an envelope, which is what I've done here. And you can see that the blocking temperatures depend upon grain size. So I've gone here from 20 nanometers up to 80 nanometers, all in the same grain size range, and they vary as a function of grain elongation as well. All right, there's a rapid increase in blocking temperature with grain size. Okay, next slide. I didn't want that slide, actually. Next one. So the other key concept upon which paleomagnetism is fundamentally based on is this idea of reciprocity of blocking and unblocking. And what this says is that if you cool a sample from high temperature and it blocks at some blocking temperature, then if you heat the sample up again, it's going to unblock at exactly that same temperature. That is a fundamental consequence of that single domain theory, and it's fundamental to the way in which we interpret paleomagnetism. Right, next slide. In this ideal situation, here we have a rock that we've gone out and collected in some exotic place in the world, and we demagnetize it, and we measure it at certain temperatures. and then we remagnetize it in a different field. We don't know what the ancient field is. In this case, we remagnetized it a little bit in some larger field. We get a larger magnetization. We remagnetize it in a larger field. But at each temperature interval, because of that reciprocity of blocking temperatures, we can plot the demagnetization lost by the laboratory magnetization gain in each temperature interval, and plot it on this diagram called an Y plot, and that will give you a straight line, and the gradient of that line is proportional to the ancient field. Okay, next slide. Now, this idea of reciprocity, of course, we will know that the paleomagnetic method is fundamental, so it has been tested. This is tested really nice paper by Dunlop on Usenet in 2001. Usenet, amazing scientist last year. And what David did was to isolate a certain region of bottom. So he had a sample, and these samples were artificial samples containing grades of different sizes, ranging from 0.6 to 155 microns. So this is not good, this is close. These are clearly not on the ones. He cooled the sample down to 370 degrees in 0 field, switched the field off for 20 degrees as it was cooling. When it got down to 350 degrees, turned the field off. So all the samples should have blocking temperatures between 350 and 370 degrees. So if you heat them up with those grains blocking temperatures, you should see what is shown by this red curve. You heat it up, which happens, and then you should spend a lot within that temperature. What he found was that actually between 50 and 90% of those minerals unblock either below or above the bottom temperature. So a huge system. And consequences for these arrival blocks. If you have this perfect single domain situation, you get this red line, you can take the gradient and turn it into the base. Every other situation, will be these curves in the right box, and you can take the gradient here, you can take the curve. So you straight away you can understand why such a large shaft scatter into the information on this slide. So what we want to do is explore that thermal state using now what we know to be a multidomain structure, which are these vortex domain states.
10 minutes.
Yeah, I should have concluded. Okay, so we can do that using a technique called dimensionalized grant, and it's simply a technique for us to have mid-dimension these domain states. If that gives us less energy, we can determine the relaxation. We did this some time ago with a colleague of mine, Leslie Nagy, who is now lost in Liverpool, and we found that the stability of single vortex domain states as shown by this red line, and here as well. The analytics in the main theory is from this black line, so it seems quite different. Two major theories thinking about this paper. One is that the single vortex states are incredibly stable, capable of holding and recording in excess of the age of the solar system, something in excess of the age of the universe. The other amazing thing is that it's not monotonically increasing, but there is an unstable zone of magnetic recording, and it occurs between the domain states. Transition from the single domain to single vortex. You have a different stability. Now, those graphs you just saw were done on the basis of the simplest possible vortex states. But of course, in real grains, there will be multiple axes of stability. So rather than having a single vortex, if you say have a elongated grains here, then you can have a single vortex that can be oriented along the long axis of the grain, for instance, or can be oriented along one of the short axes of the grains. So you have multiple different possible states. And what's more, the strength, the magnetic strength of this grain depends upon its orientation. Since the remanence is carried in the vortex core, if you orientate the vortex on the long axis, you have a larger remanence in that grain, and you do across a short axis, single-domain grains with invariant rotation. Okay, next slide. Now, if you look at the absolute energies of this, then it looks pretty imperceptible. What you find is that the preference, energetic preference of these domain states changes as a function of temperature. And most people say, well, that's pretty insignificant. If I got two data sets, I'd say they were, I could say they were again. But in sort of quantum partitioning of energies, this is a really, really significant difference. And changeover occurs at about 164 degrees centigrade at lower temperatures. The short axis grains are occurred at higher temperatures. The long axis grains. So this is quite a complicated diagram. I've got 5 minutes left. I could probably spend 40 minutes just on this. I'm not going to do that. But what we can do is very particularly, we can look at all possible transitions that may occur. So we can look at transition that might occur between one short axis and another short axis, a long axis and a short axis. And what you don't see here is actually a long axis and another long axis, because that always goes in the short axis. But you see this complicated transition relationship as a function of temperature for different grains. And for the next slide, I'm going to skip some slides. And the next one, maybe. So the significant thing to show here is that you end up with different domain states, depending on how fast or how slow you cool the system. And that in itself is significant. So here, for instance, we're cooling, say, over a million years. This is an extraordinary of 105 minute natural systems. But what this shows is the first grains become stable goes along the short axis. You get a relaxation time that's longer than the observation time, and the short axis grains will be deferred. The next slide. Oh no, go back one. Yeah, the slow cooling one. The first domain state that becomes stable are those along the long axis. And so fast cooling will end up with grains that are predominantly lying along the long axis. The problem is when you do your experiment in the laboratory to try and elucidate what the geomagnetic field is, you're always using heating and cooling rates of about an hour. So when you heat your sample at an hour, the first things that can become unstable are going to be these short line grains, and you may or may not have short line grains there, depending upon the temperature and the rate that you usually cool that. And also, you may release some grains. So if you heat it up a little bit more, you may release short grains that become allowed to flip into the long axis, which you then remagnetize at higher temperatures than you can experiment. And you end up with this huge magnetization, which is seen on the lower. Next slide. And this, yeah, let's go back one. So the two differences between single-domain theory and single-vortex theory is that we have, in certain cases, this failure of reciprocity magnetization. Single-domain grains, you could have a single-domain grain with multiple different orientations, but you have one failure orientation. Single-domain grains can change the most favored state as a function of temperature. In single-domain theory, the magnetization strength is independent of orientation. It's uniformly magnetized, and not much regular it's going to the same magnetization. That's also not true for single-vortex states. All these things together, next slide, you can put into a big matrix called a Q matrix, which simply tells us all the different domain state transitions that are possible. And that gives us a probability density. All of that probability density as a function of time and temperature in any magnetic field. We put in a bias magnetic field that tells us what we're trying to is that we can model any thermomagnetic distributed light for the sample containing these experiments. Next slide. Let's skip that one. So this is what we would like our single-domain theories to look like. This is the single-domain theory says it should look like. Next slide. This is what single words theory is. This is the worst case scenario, showing a massive change in cooling rate between the laboratory field and the Asian field. I don't have details to go into the reasons why we get this particular behavior in terms of the PTR. It's all explained essentially in these relaxation curves that I showed you earlier. Next slide. Even when you have cooling times that are similar to the laboratory cooling time, you still have significant curvature. Now, this curvature in the right plots are shown here is a real common problem in paleontology. People think that it's due to some viscous effect or some chemical operation. In fact, what I'm saying is that it's not. It's intrinsic to the very beginning particles, the physical properties of the physical particles, even in their most perfect state. Other features like this force are also very common. And last slide. Next slide. So this is a real sample from a top of a sample from Hawaii, continued by Brendan Sich, also known as the world. Yeah. And we don't see super. This is a little bit of a curvature you can see here as geomagnetic, which is predicted from some of the models that we have. So I have, that's it. Next slide, just a few conclusions. So I know it's been a real gallop, but the conclusions are that these multidomain states probably dominate the most natural paleomagnetic sample, whether it's a meteoritic sample or sample clouds from Earth or anywhere. They are almost certainly going to be these void structures. These void structures, good news is they're really, really stable, but sometimes they're not that reliable. Next slide. Problem arises where you have multiple different domain states, similar energy bands. And not only that, you have different domain states, similar energy bands, and different resulting ionization degrees. Next slide. If you do that, you get these dramatically different ionization times, and you end up with those divide plots that are just uninterpretable. So, I probably have another slide here. So, I can't remember what the critical thing is that these models I've shown you show the worst case scenario. Now, that can't always be the case, because if I take it out, I heat it up in the quality field, cool it down, and then put it through the measure technique, often you get a really good result. These grades are going to be a problem, but the extent to which they're a problem depends on the exact grade size distribution. Chances are, what you don't want to have are, if you go back on the slide, this crossover part here, where we have different domain state transitions all crossing over at a similar temperature. This is a really bad situation. If that crossover point could appear or well down here, then they would likely be real. You cannot have a paleomagnetic experiment that cycles back through this crossover point, because that will result in terrible runoff. The problem for us at the moment is we don't know which grains are in this region and which grains in this region or which in the other. And that probably goes up to something that we're going to next week. Thanks, Josh. Sorry.
No worries. No worries. Thank you, Wayne. Questions from the audience?
I'm very curious because I'm curious about the variation in the direction. So I assume it's uniform magnifies shape single domain interface. And then is the vortex a little bit more influenced by the field?
Actually,
more reliable.
That's right. actually, in terms of paleo-directional information, they're both equally as good. So this problem here of this blocking and unblocking, it really doesn't. It's only when you remagnetize it. When you put in paleo-directional work, you're not really into the remagnetizing. You're just looking at the changing direction, which is demagnetizing. And I do have a directional plot for these simulations, but this issue doesn't influence the paleo-directional. Anyway.
Okay, I was wondering, for geologists, give some examples of which minerals would have the simple plates as an one, and which are the more difficult.
That's a really important problem to solve. And my guess is, because we haven't done the simulations for a whole range, we should have it just been lazy, looking at other things. Materials that have a really high, well, one case would be materials that have a really high anisotropy that do have these linear structures, such as pyrrhotite and some degree hematite. They have low magnetic signal, but they're probably going to be quite, well, they wouldn't have this, they have other problems, they wouldn't have this problem. In magnetite, so for really common minerals that are the majority of the magnetization in terrestrial rocks, so magnetite and phytomagnetite, my feeling is that you have highly elongated grains with aspect ratios maybe of 2 to 1 or larger, these needle-like grains. Those are almost certainly going to have one dominant mainstay, and that's along the long axis. We may be able to move with the mainstays in all directions, but the energy difference will be massive. And so you have a predominance of one mainstay. So that's what you want to ensure. So a highly elongated grade would do that. That's great for phytomagnetites because they grow in, you get exsolution of when a magnetite is formed, you get the exsolution of ilmenite and magnetite. Then you can get these needle-shaped magnetite grains. And that might be the basis of the larva that you get in certain larvas. So the chilled margins of lavas, where you get the rapid cooling, and they don't have a chance to get these needle-like structures, they're probably going to be the worst. Traditionally, where the geologists go, they go for the easy samples. You know, what you going to do? You have a drill, you take the surface up from, which are probably going to be the chilled parts of the lava flows, well, depending on where you are. So there are lots of factors, and we're still in the early stages. But my guess would be look for elongated grains.
I actually consider that question well, because the sampling process is even more selective now, especially when I think even of sedimentary rocks, where even exposure we have these different types of rocks, and we have not only recognize the settling of those domains, but also then of domains. So asking practically what kind of samples.
Well, sediments are a whole different ballgame again. Just to get reliable paleointensities, you must in place in the laboratory a magnetization the same way as it is in place. You can't do that with sediments. The best you can do with sediments is have this relative paleointensity, subject to my next ground application, maintains every year. But I think sample selection is a really difficult problem, and so my personal preference is for work such as Roger Fudu in Harvard does, and John Tarduna, opposite sides of various arguments, where they are looking at the microscopic mineralogy of the sound, and they're really looking at the individual areas and their characteristics. And John Tarduna, for instance, he looks at magnetization in single crystals. Just amazingly difficult experiments to do. And there are new apparatus coming out all the time. The big thing these days are the quantum diamond microscopes. You have quantum diamond microscopes? They're not that, I don't know, they're not that expensive.
It's not that expensive.
Anyway, the quantum diamond is basically like this magnetic force microscope. You scan the surface of the sample, and it's a doped diamond in the sense of the surface magnetic field pattern of the sample. But looking at individual grains, looking at the morphology of things, really understanding what is the characteristics of the individual grains. So I don't do any of those experiments, those complicated experimental things, or stick to my simple theories. And I think it's really pointing in a very clear direction that you want to stay away from grains whose morphology indicated that multiple different states. And even now, I think most people would say that you have single domain with one domain state. You have these vortex states, and you think that's one domain state. It's not really. And then you have multi-domains, which so I would say microscopy,
Really nice and sedimentary rocks, when the grains start breaking, you might lose the grains that were present in the past, but then you didn't have remagnetization that might take them into account.
well, that's another problem of aging. And there was a very nice paper by Lisa Torps from Scripps, a rather complicated paper. She had these samples which she aged for like 2 or 3 or 4 years, and then people have the patience to do that. And then looked at the magnetic in stability of these grains before and after aging. And I can't really remember what the solution was. There was a big difference, but it was very complicated. Some behaved in contradictory ways, but it must be due to, over time, some of these particles pass and then having completely disappeared. Yes.
Well, leading on from the sedimentary question, so I completely understand it's about full magnetization stuff. Could you obviously take into account what the experience? At what point do you think that you would remove the information of the source areas? Some sedimentologists don't particularly put it back on the field, you use the source area, information about that, or simple sediment. So, did it give you quite important information about the generation of that source area, the material of it, or did it be lost?
Yeah, no, I see too. Well, you know, it depends on the exactly what the mineralogy. I think that's the answer to almost everything. But no, I think the fingerprint of source magnetic field, I think it depends what your possible sources are and how different they are. You know, and often that's, well, sometimes it's about grain size, sometimes it's about mix of mineralogy. And different mixes of mineralogy, I think, is probably distinctive magnetic field anyway, even the influence by this.
Going back on the relations the scope, I'm not sure if it's a good question, but what about pressure effects? And you know, if we think about rocks throughout in history, which is and a lot of the times we use think that pressures effect on the but active numbers have a lot of information, a lot of temperature changes, right? Pressure changes, even within the magnetic, right?
So pressure is a really interesting problem. So there are 2 effects. One is the hydrostatic pressure. That is a complicated thing to model. Gosh, my guy's name just going to my head. This guy in Munich. His name now. Anyway, he's been doing this experiment of hydrostatic pressure on magnetic signal, and he's seen this strange effect that you compress it, magnetization increases. You decompress it, magnetization is still. The problem with me is I'm not clever enough to model that because there are quite complicated mathematics. So much simpler case is linear compression or linear strain, tensile strain. And there is something I'm working on together with Adrian, who will probably come up and talk in a few months' time. He might well talk on this, I'm not sure. And we've seen that in the within tens of meters of a fault path, when you compress a rock, approximately compressing tensile strain, that is sufficient to remagnetize rocks, even without moving. And actually, it could be a way of doing some previous technology, which we have a record of very strange things. So there are definitely pressure effects, deep pressure effects in the mountain. Definitely love to stick. I definitely have to go back to the lectures.
Awesome. Well, thank you again. And we will be back next week over in the Malema. I'm not sure. Is Andrew Walker as our next talk? Yes. So we'll have Andrew Walker doing some, speaking of mantle. So,
Thanks
all
for
right.
inviting
So
me.
thank you very much.